So my name is Mohammed, and I'm going to present some of our work on capacitive deionization, which is basically it's usable only for brackish water treatment, very low salinity compared to RO, which is much better for seawater, and of course membrane distillation, which is very, very efficient for high salinity. But I'm actually going to talk about the last part that we have done with capacitive deionization, which is the incorporation of nanomaterials, mainly zinc oxide, to enhance the efficiency, rather than the overall application of capacitive deionization. So we all know the deficiency in water that we have, and of course in the Middle East we do a lot of desalination. We actually, in Oman, 96% of domestic water is desalinated seawater. That's 96%. And that's why, of course, RO is very strong in the Middle East. But the problem with that is it is so, we are still what we have done basically is we started with RO, we started with MSF and then with RO, and we forgot that there are a lot of other sources of water that we need to take care of. So I'm from Oman, so I'm going to talk more about what we basically have in Oman and why do we need other different processes of desalination rather than RO, which is of course what we do basically in Oman. They actually, as a government policy, from 2015, they basically said no to all kind of desalination processes except RO. So all of the desalination processes of Oman now is RO, but they want to make a study on is it really the right choice that they made, and is there a possibility of going back and on this policy and see if they can do something else. So as you can see over here, about 90% of water used in Oman is brackish water or fresh water, groundwater and surface water. So yes, 96% of domestic use is desalinated RO, but that only constitutes of basically about 4 plus the left 5% of the water used in Oman. So instead of concentrating on that, we also need to look at this part over here, which is very important for us. Now, this exacerbated basically because we are experiencing seawater intrusion in Oman. This is Al Batina region in Oman. It's the most agriculture. We have the highest agriculture. It actually has 50% of our agriculture. And because it's on the sea and because of all of the extraction, water extraction, we have seawater intrusion. So the salinity, you can see that the salinity over here increased by a huge margin. There is even basically brackish water that is 27,000 ppm, which is close to seawater desalination rather than brackish water, actually. So this is what, in general, what we have is most of the desalination plants worldwide is RO, and because it's RO, it's because what we do is we desalinate seawater. So seawater comes with it RO. But if we look at the other types of waters, then we probably need to look at something other than RO. And this is what's happening because we have in Spain and other countries, they do electrodialysis for river water, which is basically a very good thing because there is no salt in there. We don't need to salinate it. So capacitive deionization, which is the title of the work in here, consists of two steps. One is the desalination process, the other one is the regeneration process. So in the desalination, we have two electrodes, we have the circuit, and if we basically close the circuit, we have the positive electrode and the negative, and we introduce the water in it. And what we have is basically the sodium or the cations will go to the negative electrode, whereas the anions will go to the positive electrode, and we have desalination. And because of that, the higher the surface area, we have the higher the electroabsorption, and therefore we have higher desalination. The next step is the regeneration process, and in that we basically have reached the saturation of the electrode, and therefore we need to regenerate that electrode. We need to remove those ions so that we have another desalination step. So what we do is basically we short circuit or we reverse the polarity, or short circuit, which I'll talk a bit about it later, and all of the anions and cations will go into, will leave the electrodes. So these are the trends of CDI. These are the papers or publications that were produced. And you can see that electrodes is the highest one that has around 300 publications on electrodes, rather than the reviews and ion exchange membranes. Using it as an exchange is very low. On the other hand, there is a high increase in the publication in the field of capacitive deionization. And the reason why is because CDI exhibits lower fouling compared to RO. Of course, we need more studies on this, on real water with different faunas, to see if that is really true in all of the cases or if it's very specific. It requires no pressure. And if we use a very good electrode, then we don't expect the deterioration of the electrode. So it's stable, much stable than RO membranes that has a lifetime of 3 to 5 years, even though they say that it's 5 to 7 years. Some of the limitations basically is, of course, because it relies on electrical polarity and charge, it can only be used for ion removal. So if there is non-ionic molecules in there, they will not be removed. So all kind of other things, some of the emerging contaminants, organic contaminants, this will not work in it. Probably also some of the produced water, the oil in water, that is also not a really good, not good for this kind of use. And the reason why it is used basically for low salinity, because the higher the salinity, the higher the power consumption. And therefore, this can only compete if we are working with low salinity. Once we go into higher salinity, higher than 5,000, 7,000, 8,000, then RO is much better than it because it gets saturated very easily. This is a typical cell for CDI. And we basically have the collectors over here. We have the inlet and we have activated carbon cloth. That's what we use in our lab, activated carbon cloth, because it's very cheap, but also with other things that I will talk about. And one of the things that is very important is we have an applied pressure of around 1.8 volts. We have actually tried higher volts, maybe, because, but with that we get hydrolysis. And with hydrolysis, basically, you get a lot of bad things. We have done it for phenol, and we got chlorophenol, which is much, much worse than phenol in that regard. So we stopped our research on that. So activated carbon cloth has very high specific surface area, which is exactly what we need. High conductivity, low cost, high flexibility, high stability, and it's widely available. This is the cloth, which is basically very similar to what we are wearing. Because we are in Nanotechnology Research Center, we would like to do more on nanotechnology, nanomaterials, and advancement of this using nanomaterial. So what we use is basically, what we use mainly is zinc oxide, different nanomaterials-based zinc oxide. It's because it's biosafe, it's environmentally friendly, naturally hydrophilic, and it's an N-type semiconductor. This is how it looks in. These are nanorods on the carbon, activated carbon cloth. And this is this is where we began with this, with the nanomaterials for CDI. And we basically, this is the pure ACC, and we have done zinc oxide, basically nanorods at the surface. We have grown for 5, 10, and 15 hours, and you look, the efficiency increased up to a point, and then there is a high decrease in efficiency. That's because of the blockage of the micropores and the mesopores. The main place where deionization happens is with micropores, in the micropores. Mesopores are not really active in this regard, but because of the high increase and the longer that we have the zinc oxide, the lower the efficiency after a point. So we are increasing the surface area, but also blocking the pores of the ACC. Skip that. This is basically what we have done. What is the for the height of the nanorods, and if you see the electric field of the dielectric, basically the dielectric, that surface charge is basically only at the in the inset over here. It only happens at the base and at the tip. There is no electroabsorption at all of the middle part of the nanorods. It's only in the surface, again, at the bottom and at the tip. This is what happens. And we basically did a modeling for different kind of nanomaterials. And of course, because zinc oxide and silicon oxide, they have a much lower dielectric, they were much better compared to titania and zirconia. And this is basically what we have done with the flow modeling. It's basically, this is where it happens. This is a zinc nanorod on the ACC, basically. And therefore, this is where we have the dielectric. This is where we have the electroabsorption. And again, only one nanorod is much better, is preferable compared to many nanorods. And that is because the nanorods are not really vertical, 100% vertical. It's basically, they go everywhere. So again, we are basically reducing or increasing the dielectric in that area. And this is another part, basically looking at the microsphere and the microsheet of zinc oxide. This is how it looks on the ACC. And again, we have the highest absorption is basically with the nanorods and the microsheets. And that's again returning back to the shape of it. This is where, again, at the tip and the bottom. And therefore, we have higher surface area here compared with the microsphere. And that's why we have higher absorption and we have higher salt removal efficiency. We have tested this for brackish water. We use different brackish water for this. This is one of them. And you can see that the conductivity basically dropped with time. Of course, this is a time-dependent desalination compared to RO. And therefore, the more time you do, the longer you do, the higher the desalination. And therefore, once you decide on what is basically your output is going to be, you stop the desalination in there. Except, of course, if you go to the saturation where you basically saturated the electrodes and now you have to regenerate. And of course, we tested this also, and you can see that the calcium is much higher. The electroabsorption of the calcium is higher compared to sodium. And that's good because we have a problem, of course, brackish water. The main problem with desalination of brackish water is actually the hardness. The calcium, the carbonates, magnesium carbonates. These are, with RO, especially in Oman, we have highly hard water. And therefore, RO basically stop with the recovery with that because of the hardness rather than the salinity. And therefore, with this, we have much higher efficiency for the removal of calcium in comparison to sodium, which is again much preferable than for brackish water desalination. The other thing that we have found out with the CDI is basically it is not a real disinfectant, but it is biocidal. And it's biocidal for two ways, because the microbes, they get killed by the electric field. But we also have the absorption or the electroabsorption, of course, of the microbes at the surface of the cloth. And therefore, again, it's not disinfection, it's 100% killing or removal. But you can see that this is the feed and this is the desalination is much higher. So it does have a biocidal activity, which is a good thing, but we still need disinfection after. We have done a bigger design for this, basically to see if how efficient that can be in a longer run rather than only a couple of hours. So we have done testing for 30 hours, and these basically are generation of desalination regeneration steps. Each one of them is around 30 seconds because the salinity is quite high. Because of the salinity quite high, we don't want to get to the basically we don't want to get to I forget the term now. Anyway, saturation. Very good. And you can see that this here is for synthetic water, which is very good for the whole 30 hours, while for the well water, we have a decrease in the efficiency. That could be on two, which is one is the divalents like calcium and magnesium. They are harder to remove in the regeneration, but also because we didn't do any kind of pre-treatment. And therefore, we have the STI, the turbidity, that will affect the system because they will settle at the surface of the electrodes. So what we have done is basically we've done a quick cleaning with citric acid with sodium hydroxide, and you can see that the efficiency is much higher in comparison to no treatment. And this is the last, basically, test that we have done, which is the possibility of using this for what we can consider as industrial wastewater, like mining water. And we took two, basically, heavy metals, cadmium and lead. And again, what we have done is we've done zinc nanoparticles at the surface of the electrodes of the carbon cloth. And you can see that basically each one of them, they have a very similar power consumption, but the ion absorption capacity of the zinc oxide with the carbon cloth with the zinc oxide is much higher. It's about double that for both of the heavy metals. So we expect the removal of those two heavy metals to be higher with the zinc oxide carbon cloth. And so we have done the trials, our trials. We have around 50 minutes of desalination. 50 minutes of desalination. And this is one of the tests that we have done previously, which is basically, do we do the polarity change for the regeneration or we short circuit? And we found out that the most efficient one is basically we short circuit for a very short period, we change the polarity for a small period, short period, and then we short circuit for the other part because the desorption happens at the beginning. And this is basically what we have got for lead, about 17% removal with the carbon cloth, and 33% with the zinc oxide enhanced carbon cloth. So much higher removal with it. But what we found out basically is the physisorption of lead is higher with the activated carbon cloth. Physisorption is the normal, of course. We do this basically, we put the carbon cloth, the lead water, basically solution, all night, 12 hours, to make sure that there is no adsorption. It's already, the level of it is already saturated without any electrical current, so that we don't take adsorption in there. And so physisorption of lead is high, while the electrosorption is much higher for the zinc oxide. And for the cadmium, Again, it's the same process. What we have is basically 20% removal with activated carbon cloth and 29% with zinc oxide activated carbon cloth. And which is we have done this quite a few times to make sure that this is still there, because if you see, this is 21 with 29, while the other one is basically 17 and 33, which is one is higher than the other. And what we found out, and if you look at you look at this, with lead, we have very high physisorption. So basically what happens is, as you run the current, because of the physisorption, as you run the current, we have a backflow, back diffusion of both the lead, and this is lead nitrate, both of them from the surface to the bulk. And that is because, of course, with the physisorption, there is no current, and therefore both of the ions, cations and anions basically settle at the surface, absorbs at the surface. And so basically what we have at the beginning is we have a high increase in the salinity, which is basically a back diffusion, which is not expected. And this happens with lead, with the activated carbon cloth. While on the other hand, with cadmium, it's quite the opposite, because now the cadmium the physisorption is higher, but the lead electrosorption is higher, and therefore what we have is basically the back diffusion is at the regeneration part of the zinc oxide enhanced cloth. And so basically what we have here is, once we change the polarity, it takes very short period, within seconds, to regenerate the electrode with respect to cadmium compared to lead. And I think this is the final one. We have done a prototype for this. We also have a patent on another electrode, which is basically 3 electrodes. So this is 10 liters per day prototype that we have done in-house. And it showed a very high, it's very good efficiency. We didn't really compare the efficiency of this with RO, but hopefully we can do that in the future. And with this, I end my talk. Thank you.
Thank you, Professor Mohammed.